Working Group 145 is concerned with chemical speciation modeling, which is widely used in analyzing and interpreting interactions of seawater with the biota sediments of the atmosphere. Almost all published modeling results use individual models that lack full documentation of the model parameters used and their sources. Our goal is to address this problem with freely available software set out in our vision. The introduction of full documentation and uncertainty estimates is a major step change in this field. Our progress to date and future plans are summarized in presentations by working group members who lead the different parts of the project.
The users of chemical speciation models span a wide range of disciplines, including academic and non-academic practitioners. So there is a need for a user-friendly, flexible model that can accommodate broad applications. In its first year, the working group convened a town hall meeting at the 2016 Ocean Sciences meeting and conducted surveys to query the needs of both academic and non-academic model users. This feedback has since shaped the development of the speciation model. The majority of our users have interests in the ocean CO2 system and trace metal applications. So the speciation model has prioritized these applications, and we've engaged interested members of the community through international networks such as OCB, GeoTraces, the Global Ocean Acidification Observing Network, and the Marine Knowledge Exchange Network. We've convened tutorials and disseminated information via flyers, and most recently at Ocean Sciences 2020, tutorials, demos, and establishment of an email list of users. In addition to these user engagement tools, we've used our website, which is shown here, to share working group progress and outcomes, which you'll hear more about throughout this update.
Speciation models for natural waters. Conventional speciation models are generally empirical. They calculate speciation for given salinity, temperature, and concentration variables for the system of interest. CO2sys for the marine carbonate system is an example. These models are based upon measurements in seawater of salinities and temperatures covering the desired range. They are not valid outside of the measured ranges or for other natural water compositions. The alternative approach is an ion interaction model in which activities of all dissolved species are modeled as functions of temperature and the concentrations of the individual solute species present. We're focusing on models that include first, the solute species present in artificial seawater, and second, in standard seawater. We have implemented models 1 and 2 on the slide, extended to include tris buffers for the calibration of pH instrumentation. Calculations can be carried out with these models for waters of arbitrary composition. So what we have done. 1, our starting point is the 2 Miami speciation models of Piero and Malero and Waters and Malero. 2, we've added the propagation of uncertainties in equilibrium constants and model parameters through to the calculated speciation. And 3, we have created draft traceable speciation computer codes for total pH and carbonate speciation in natural waters. These estimate both total uncertainties of the calculated speciation and also all the individual contributions from different equilibria and solute interactions in the model. And these capabilities enable us to identify elements of the model that need improvement. It has resulted in a program of experiments to make thermodynamic measurements to improve the model of tris buffers in artificial seawater, and this is an addition to our SCOR project. Let me take you through some results. A calculation of the values of the carbonate stability constants in a salinity 35 seawater that has had its composition altered from normal stoichiometry. This is the output page of the draft model. The input, starting at the top, is a salinity 35 seawater for which has had all sulfate removed. The model calculates 1. The change in pH associated with removing sulfate, which is 0.1, and the associated uncertainty, which is 0.005. 2. The changes in the 3 log K star for the carbonate system and their uncertainties. 3. The individual uncertainty contributions to each of the calculated quantities, which is useful for model development. And finally, 4. The easy part, which is the species concentrations.
So why is this work important in marine science? Well, a clear example is the growing recognition of the phenomenon of ocean acidification and its potential implications for marine ecosystems has made the measurement of pH an important feature of a wide variety of research and monitoring activities. For example, the proposed indicator for the UN Sustainable Development Goal, SDG 14.3.1, asks for the average marine acidity measured at an agreed suite of representative sampling stations. And there's a broader desire that such measurements be of known uncertainty. As a result, IAPSO has recently sponsored a best practices study group to address these needs. It's chaired by a Working Group 145 member, Andrew Dixon, myself, and the Working Group 145 co-chair, Simon Clegg, is also a member. The primary aim of this study group is to articulate a best practice for seawater pH measurements in the context of our present understanding. The primary linkage to Working Group 145 lies in understanding the current state of the art and in indicating the work that may still need to be done to ensure an approach that is at once of known uncertainty and which places seawater pH measurements in the wider context of naturally occurring aqueous solutions. Another related and close link is with the task group on seawater pH of the Joint Committee on the Properties of Seawater of the International Association for the Properties of Water and Steam, IAPWS, SCOR, and IAPSO. This task group also consists of both metrologists, largely from the various national meteorological institutes, and marine scientists. Its aim is to articulate a clear definition of seawater pH that is at once consistent with a conventional definition based on measurements with Harnett cells, and that can, at least in principle, be shown to be traceable to the International System of Units, the SI. This requires both a careful metrological understanding of the process of pH measurement, as well as a defensible way of estimating the uncertainty inherent in interpreting Harnett cell measurements in seawater media. And this in turn requires a well-defined model of activity coefficients in such media which has a clear description of their uncertainties. As noted earlier, it is this latter aspect that is being addressed by our working group.
A pH buffer characterization. So why are we focusing on modeling pH buffers for seawater? Because salinity and temperature coverage remains limited, in particular very little below 5 degrees centigrade and nothing below a salinity of 5. Also, there are limitations to existing approaches. First, the transition to freshwater remains a problem, and second, the presence of other ions can only be accounted for by making further measurements. The speciation models that we are developing can potentially overcome both limitations and improve the traceability of pH to SI units. And we have started a program of measurements to improve and develop the model of the pH buffer. The experimental program that we have been able to add to the project to improve the model of tris buffers includes oceanographers at GAMR in Kiel and 3 national metrology institutes, all of which have an interest in pH, pH standards, and the traceability of pH to SI. The experiments include solubilities in aqueous tris salt mixtures, these are complete, and experiments in progress that are Harnett cell measurements of HCl activities in aqueous mixtures. These are being carried out at several institutions, and the work in Japan is also already complete.
We are extending the draft software that presently focuses on pH buffers in the CO2 system to include minor and trace elements, an important application identified in our user surveys. Among the minor elements, we include silicate, which is often omitted from PITSA models The trace element work begins with the geotrace's core elements, but not limited to them, and includes not only the inorganic speciation, but also complexation by competing ligands used in titrations. These involve a three-way competition between inorganic ligands, natural organic matter, and a competing ligand, as shown in the left-hand diagram. The right-hand diagram shows some titration curves. Quality-assured speciation modeling will enable accurate assessment of the metal-natural organic matter interaction. Natural organic matter is a new initiative that is at an early stage and may not be ready for inclusion in the 2022 launch. At high concentrations, natural organic matter has been shown to contribute to seawater alkalinity. It is also the focus of the titrations described in the last slide. Natural organic matter presents a considerable challenge due to its polydispersity, as exemplified by the broad distribution of pK values as compared with phosphoric acid with just 3 pK values. We are now exploring the use of an integrated PITSA-Nicodonon model with an initial focus on two areas: the contribution of natural organic matter to alkalinity and its complexation with trace metals.
New initiatives, a GESAMP working group. GESAMP, the group of experts on the scientific aspects of marine environmental protection, is an advisory mechanism to 10 sponsoring UN agencies. A new working group on climate change impacts on contaminants in the ocean has been initiated. It will be co-led by the IEA, UNEP, IOC UNESCO, WMO, and IMO. Deoxygenation, ocean warming, and ocean acidification are all impacting the speciation of contaminants like trace elements, radionuclides, organic pollutants, and nutrients. However, the extent of these top-down effects is not well qualified yet, and knowledge is necessary to inform impact assessment models. This working group will start in 2021. The expertise of SCOR Working Group 145 is of paramount importance for this new GESAMP initiative, and the chemical speciation model will be an essential tool to calculate changes in the speciation of contaminants.
This slide summarizes our progress and plans. We have put significant effort into communication with the community so that the 2022 software release should not come out of the blue. Code development is on schedule for the 2022 launch. pH and buffer modeling has led to a broad collaboration with national metrology institutes and with the Joint Committee on Seawater, where we contribute to the goal of a seawater pH scale that is SI traceable. Work on minor and trace elements is now underway and on schedule for the 2022 launch. The work on natural organic matter is currently in an exploratory phase. And our expertise is essential to a new GESAMP working group. We are well aware that we have used our full financial allocation from SCOR and that we are a relatively long-lived working group. Our working group proposal made clear that we would need to raise significant funding in order to achieve our goals, and that this could result in some delay, which was indeed the case. However, we now have good funding from a joint US-UK program and have received extensive in-kind research support from a large number of institutions. We plan to launch our software product in mid-2022 and request that we remain an active SCOR working group until that time. We believe that this would benefit SCOR by identifying the software as a product of a SCOR working group, while SCOR's prestige will help to ensure widespread use. Thank you for your attention.